there's more value in the connections outside of these talks than actually listening to the talks themselves. Like, we've spoken to a lot of very experienced, very tenured people who have lots of, great stories and mistakes that we can learn from so that we don't have to make them as well.
Good afternoon, everyone, and thank you for coming to this talk. I'm here to talk to you about behavioral modeling in hardware-software co-design using C++ coroutines. My name is Jeffrey Erickson. I work in hardware-software co-design architecture at Intel Corporation. I work in the Programmable Solutions Group, which is the FPGA portion of Intel. And I'm here today to tell you a story about a problem that we tried to solve, and we solved it in a way that we think is fairly innovative. And I hope that through telling you this story and showing you some examples of how we applied coroutines to our problem, I inspire you to take a leap and try something different, some new language feature that's cool and exciting, and see what you can leverage from that. So about this problem. We're on the embedded track here. So imagine, if you will, a scenario where you're an embedded developer and you're getting a new piece of hardware. You could be working for a silicon company and that piece of hardware is deeply embedded in a chip. You could be working for a board level company and you have a new peripheral you need to interact with, but you don't have the hardware yet. Your timelines are tight and you want to be able to work on the software sooner. Well, I call that shift left. There's other organizations that call that shift left. And the basic premise is, let's get a model in place, hence behavioral modeling, earlier in the process so that you can start your software development. The reason is, if you wait for the RTL to show up, if you're a deeply embedded developer, or if you wait for the board to show up, if you're a board level developer, you've missed the boat. You are too late. You should be writing your software well before that. And our suggestion here is that you want to use a transactional, behavioral, or functional model to do that, and coroutines are a way to implement such models. We'll talk about why there are advantages there. So what's this model? What's the thing that we're trying to build? Well, we're really just looking for side effects. So a model has an operation that will trigger side effects. Could be a read side effect, could be a write side effect. Something occurs when you transact with the model that changes its state. So you catch that side effect and define it and change the model state. And then at a later time, you can do a different transaction to inspect it and observe it. And on this note, I want to emphasize the level of detail that's required here. We're not talking about something that is clock cycle accurate. You need RTL simulation for that. You need the actual board for that. So let's do a comparison here, considering a public key cryptography accelerator. So we're talking about a signature generator. I picked a security element. This applies to other ideas as well. When you use the hardware and you write to your registers and you cause the hardware side effects, there's a whole bunch of complex hardware stuff that's going to happen to make this cryptography action occur. And that's going to cause a result after some amount of time. And from your perspective as the embedded developer, you're going to see a go bit become ready, or you're going to see a done bit get set. Everything that happens in between, that's hardware's job. So what you really just need is an OpenSSL call. You need to have a register interface that lets you trigger that OpenSSL call, get the results, and put them in your registers just like you would expect with the hardware. But you don't need all the detailed timing interactions that are required to make the hardware operate. When you consider increasing the complexity of this model, so we started with this OpenSSL call, what happens when you add additional peripheral interactions? So for example, the keys that are involved in cryptography are often considered very sensitive, and there are hardware protections for them. I call it a key manager. For you to actually test your software to do the signing operation in this cryptographic example, you would need to manage the key manager and manage the cryptography engine. Therefore, your model needs to reflect the back-end interaction. And I've just made one extra level of complexity, one interaction where two different pieces of hardware have to talk to each other, and you as the embedded developer responsible for writing the software to do it. What happens when this scales to 3, to 5, to n? You end up with a large complexity, and writing that model is not an easy task. How did we address the complexity concern? We used coroutines. Coroutines are an enabling language feature. They're a way to write code that looks more like RTL. They provide syntactic sugar for things like state machines, where your RTL folks will see the C++ code and say those things are similar. They also reduce net numbers of code. They handle parallelism in a way that isn't clunky. Now, coroutines are not truly parallel. They're time slicing, essentially. They're concurrency, not parallelism. The comment here about handling parallelism is that the hardware always runs in parallel. If you've got hardware that is parallel, it will always execute in parallel. This gives you a way to provide that appropriate level of detail in your software interaction in a way that isn't clunky. And, as I mentioned, they're more scalable. We'll go through a few examples of how this occurs. The thing about coroutines is they lack comprehensive standard library support. And we used a library called CppCon. I'm not an author or a contributor to CppCon. I'm simply a consumer. I'm telling you the library I used because I found that it wrapped the coroutine language feature rather effectively. So let's talk about how coroutines are implemented. This is not a comprehensive tutorial on coroutines. I'm trying to give you a few parts of the coroutine pattern in C++ to help you understand the syntactic differences and help you appreciate the simpler code that you can write with them. So coroutines have a few new keywords: co-yield, co-return, co-await. We'll take co-await first. Co-await is the way that you tell a coroutine you need to pause execution until the argument of that co-await becomes ready. In other words, you're waiting on something, and that something is called an awaitable. A co-await can also produce a value. Sometimes it's void, depending on the definition of the coroutine that you are co-awaiting, but it can also return a value. Co-yield is inside a coroutine, produce a value, and then allow another co-await on that coroutine and resume execution at that point. And finally, co-return is the special return statement in the coroutine system in C++ that allows you to either end with void or return a value. The compiler looks for these exact keywords. If you try to return from a coroutine, you'll get a compiler error. Because a coroutine, again, it's a special language feature. The compiler handles it differently. So coroutines are about promises. And this is a promise in the sense of async future promises, that eventually the promise will deliver a result. That may be a void result. As an implementer, you will write something that looks like a function. And you'll see a couple of examples in a minute here. They are not actually functions, they're coroutines. That object, when you start it, gets scheduled by a runtime. In the case of the library that we use, CppCon, there's a few different ways that gets scheduled, but starting the coroutine allows it to run. That's the important part. And it will run until it reaches a co-await where the awaitable is not ready. And as I mentioned, coroutines are a concurrency practice or a concurrency framework. They use a time slicing model, and as coroutines become ready, they execute. And then as co-awaits become ready, the awaiters continue their execution. So, I said it looks like a function, but it's not. This is the approximate pattern. You have a result. That is the awaitable. And the result returns a type. And in this case, it's UN32T. I called it foo. It's a very basic one. It returns 4 zeros, 4 Fs. Now, you can do a lot more in a coroutine than simply return a value. I'll show you some of that in a minute. But again, it reads function-like. So from somebody who is used to writing functions in C++, you can look at this and you can kind of at a first order grok it, I hope. These can also be members of classes. So you can have a coroutine that accesses member variables of a class as a way to represent an object, like say that public key cryptography module I was talking about. If you assign that awaitable to something, you don't get the value. So if I assign, in this case, foo to bar, bar is now the awaitable. It is not 4 zeros, 4 Fs. How do you get that value out? You either co-await in the coroutine, and when the co-return occurs, you'll get the value out. Or from outside a coroutine, you can start that coroutine, and this is a syntax particular to our library that we chose to use. And after you have started the coroutine, you can later get the value out of it, where the result T type defines wait, which is block here until the coroutine that I'm waiting on completes, or get, which is block here until it completes and then give me the value. Okay. So that's super high level coroutine knowledge. There's plenty of prior CppCon and internet resources that explain coroutines in more depth. I invite you to research those and look at them. I'm going to move into the comparison of complexity between threads and coroutines. And I'm not suggesting that coroutines are a universal replacement for threads, but I'm suggesting that in the modeling context, they offer some advantages. So a lot of times when you're doing this modeling, you're waiting for some condition to be fulfilled. You've set your registers, the backend side effects are occurring, you have to get that side effect to complete. When that side effect completes, you're no longer waiting, and that wait condition becomes ready. So let's start from the basis of a thread. If I have a thread, the thread which makes that condition become ready needs to gain a lock. The thread that is waiting for the condition to become ready needs to try to get the same lock. And initially we expect that it will not be able to acquire that lock. When the condition becomes ready, the lock is released by thread A. Thread B then acquires the lock and continues execution. The same pattern in a coroutine is you have a coroutine that defines the ready logic. You then have another coroutine that co-awaits that one. Whoops, my mistake. That coroutine that is doing the awaiting becomes not ready because the thing it's awaiting for is not ready. When coroutine A meets its logical condition to become ready, meaning it returns or it yields, then coroutine B can run. What does this look like syntactically? Well, I used the example here and I chose a binary semaphore. You could also do it with mutex. You could do it with some other thread synchronization mechanism. You start that thread synchronization mechanism in thread A in the acquired state. When it becomes ready, you release it. But before you released it, after you've started thread A, you start thread B. In thread B, you try to acquire that lock. And that's where the synchronization mechanism appears. But you might realize that if you're going to do this synchronization multiple times, you have to hand the lock back to thread A, meaning you have to very carefully check to make sure that every thread that acquires a lock releases its lock, which is kind of basic threading principles. In the coroutine case, you can think of it as a one-way lock. You don't have to give the lock back because when the awaiter co-awaits again, that coroutine will either be in the ready or not ready state. If it's in the not ready state and it's still executing, you just wait till it's ready. So again, it's doing the same, it's doing a similar concept under the hood, but syntactically is cleaner. So how do threads become untenable in complex systems? And anybody who's done multi-threaded programming knows that this is a challenge. The thread locking mechanisms are designed for shared resources. Things like I want to get access to a file. So the file is normally available, there's no lock. When a given thread wants to use the file, it gains the lock. And when it's done with the file, it releases the lock. That's fine. The issue is they're generally not good at handling combinatorial conditions, meaning I need to wait for a series of locks to be to be acquirable before I'm ready to continue execution in my thread. It's not that this doesn't exist. It does. And there are language mechanisms, standard library mechanisms, which do this. But you have to realize that, I mentioned earlier, your locks are all essentially inverted. They start in the acquired state, and that means that you might need to apply some interesting Boolean logic to them to meet a complex condition. So for the sake of illustration here, I'm showing you two basic ways to do multiple locks. And both of them use scoped locks. The first one says, just give me 2 out of my list of locks, and I need to wait for both of them. But when I need to wait for 10 of them, I'm starting to run into syntactic ugliness. We don't like syntactic ugliness. Remember, we're going for a clean implementation here that a non-C++ expert can read. Here's what it looks like for a coroutine. You'd have your list of coroutines, your results, your promises, your awaitables. And in the case of the library that we used, you create a new awaitable that says when all of these conditions are met, make this awaitable ready. When all of these awaitables are ready, make the when all awaitable ready. So you can think of when all as the and condition. I've anded condition 0, 1, and 2. You can also do this with an iterator, and that's just a matter of the implementation that the library author chose, where you can give it the list and say from begin to end, make them all true, make them all ready. So a couple execution things to consider here. The first is you are still spawning threads. Don't think that the threads have gone away. The runtime may be running things in multiple threads. Deadlocks can occur when you have multiple threads running, but they're generally easier to find because, again, the code is more readable. There's no requirement to both acquire and release the lock. You're merely co-awaiting, and therefore you can usually identify, here's where I missed the, or here's the co-await that doesn't become ready. And if you follow some kind of straightforward, safe implementation patterns, you'll avoid a lot of this. So not looping without delay, no simple cycles, and following things like state machines and switch case pattern. I mention this because as embedded developers, we probably do a lot of this already. And you're just carrying your knowledge and your best practices from the embedded world into the model. Okay. So I mentioned waiting is one of the more important things to do. I'm going to go a little bit deeper on waiting for multiple conditions, the straight delay, the generator pattern, and then how you can start a coroutine using a callable. So how do you wait? Well, we already mentioned single condition, just wait for the coroutine. And in this case, A, B, and C are the parameters for the coroutine. The multiple condition and, you use this when all construct, which is just a library construct to create a new awaitable that becomes ready when all of the all of the provided awaitables are ready. And then there's also the or version of that, which is when any. So if any one of those, Coro A, Coro B, become ready, that condition will be met. You now have the and the or operations for handling the conditions of your hardware. Unfortunately, there's not an invert, but at the same time, I would argue that the modeling case where you need to have something ready and something not ready is kind of unusual. I'm sure that you could write an awaitable that just changes its state by saying I'm the opposite of this other awaitable. You can do those types of operations. Again, the library we chose doesn't support it, but conceptually, we could build with not too much extra effort the full Boolean logic operator set that we would need. So one thing that the concurrent CPP library does that is actually one of the one of the earliest examples in the raw coroutine implementations in the language is how to delay for a fixed amount of time. In this case, you have an awaitable that becomes ready through a separate thread that is running a timer queue. And as the timers expire, you make the awaitables ready. And that allows you to say, stop execution at this co-await, and then when the timer becomes ready, it'll let you continue. This is good because this is the means for delaying within loops. And those types of short delays are helpful because it allows for other coroutines to run. Gives them time, gives the runtime the ability to figure out what's ready, let's go execute those things. And you notice here that it uses chronomilliseconds from the standard library. You should remember when you're working with your model that this is a virtual time or a fungible time. And you can make milliseconds actually mean picoseconds if you need them to. It just takes a little longer for your model to run, and you can't really guarantee that that timing is strict. So if you if you create the delay, if you create the delay object to wait for 10 milliseconds, it will not become ready for 10 milliseconds. But that doesn't imply that it runs immediately at 10 milliseconds. Anybody who's familiar with an RTOS knows something about that. If you make a task ready in 5 milliseconds, there's no guarantee that it runs exactly at 5 milliseconds. It runs sometime shortly thereafter, we hope, if your RTOS is behaving well. So again, parallel concept. So I mentioned the state machine pattern as an example of a useful way to take advantage of a coroutine. And it's kind of straightforward. This one's very rudimentary, but I'm saying there's two states, state 1 and state 2. And there's a decision that's made by a coroutine called wait condition 1 that tells you what your next state is going to be. And then if you are in state 2, you wait for a millisecond and you immediately go back to state 1. So digital logic design 101, really basic state machine, but I've done it cleanly in just a handful of lines. I don't have a thread lock, a thread release, and then vice versa in order to figure out the synchronization between wait condition 1 and this state machine. And again, the suggestion I'm making is that coroutines provide syntactic sugar for these types of common hardware implementation patterns that we can migrate into software. And I would argue that your hardware friends will look at this and say, I understand what's going on. Generators. So I mentioned co-yield, and I'm just showing you a really basic implementation here that says every time that you co-await this gen uint, produce n and increment n. So if you co-await it once, you get a 0. Co-await it twice, you get a 1. You could do something more complex here. You could have this be the output of AES, where you're putting your ciphertext into that engine, and then it's producing, rather than decrypting the whole buffer, your results as you're going. Callables and coroutines. Okay. This is going to be important when we talk about how you test these things. This is similar to the future and async concept, where you tell the coroutine runtime to schedule a workload for you. Schedule this foo.wait in the case of the second example on the screen. What you're doing here is you're creating an awaitable and starting a coroutine, and the coroutine's internal behavior is the callable. And in this case, I used a lambda. So this lambda is capturing everything by reference. Conceptually, foo is in scope at the point where this is being called. I now have a thread-like ability inside my coroutine system that allows me to start multiple parts of a model or to inspect a model during a test. This is the way that you interface from the outside the coroutine world into the coroutine system. Or I should say that was our design choice. I'm sure there's other ways to do it. I mentioned before that there are actually threads underneath it all, and that means you need to account for atomicity. There is true parallelism potentially in the runtime, particularly if you use that thread pool submit a couple of times, you will create separate threads. And atomic operations at the scale that we're dealing with them generally won't hurt. You're not going to see some runtime performance difference because we're not after super high performance, very responsive code. We're here for an accurate model. So taking a little extra time to do the atomic operation is generally not sufficiently costly that you shouldn't do it. They also generally enable more scalability because from the get-go, you've built the atomicity into the code, which means as you add more dependencies, meaning you start awaiting on more of your models between each other and you're developing this network of conditions, you already have the atomicity present. The other way that you can do this is a lockless implementation. And that's actually our practical example. So I'm going to show you a coroutine-based queue. This assumes that you have a prior implementation of a queue. We're going to wrap it with a coroutine that allows you to develop a list of defined length of elements T, it's templated. When you push into that queue, if it is not full, the push completes, it's added to the tail of the list, and you immediately return. If it is full, you wait until something else is pulled from the head of the queue to make space, and then you complete. So if it's full, your co-await will not immediately become ready. And then similarly on the pop, if you're not empty, take the front of the queue, the head of the queue, return it immediately. If it is empty, then wait until it's not empty, and then return the head of the queue. So what does this look like? Well, the first order concept is just push to the queue. Except I've broken my own contract. Because the queue here, again, is some implementation of queue. Some list that has a measurable length. I'm not waiting. I'm just assuming that I can push. And I'm not really enforcing that length constraint. So I need to add a little extra logic. I need to say I can't do it yet. We're going to wait and keep trying every time that we can't do it, meaning every time that we are larger than max elements, we will take another pass through this loop. Once we have less than max elements in the queue, we're clear to push. So go ahead and push that element into the queue, set success equal to true, break out of the loop, and return. The success equals to true is not strictly necessary. You could just break there. I'm using that for like full clarity, that if you wanted to have this return bool, you could then co-return success at the end. You should therefore never return false because you would be stuck in this loop, trying to highlight the difference between how you do this outside a coroutine and inside a coroutine. In a coroutine, it's impossible for this to return false. But I broke one of the more important rules, which was don't create a tight loop. Don't have a loop without delay. So we actually need this extra little, hey, let's take 10 milliseconds before checking that queue again. And I picked 10 milliseconds as a placeholder time. It could be 1 millisecond. It could be what have you. But that's enough to say I don't have a tight loop that's just spinning. I'm making the coroutine take a break by creating an object that says you're not going to be ready for this amount of time. And then on the pop side, again, naive implementation or first order implementation, we'll just go ahead and get the front of the queue. The problem is we don't know if the front of that queue is valid. And depending on how that queue was implemented, we might be getting the last valid value, but we've actually already popped it. We're not checking that the data is correct. So I'm going to go ahead and combine the timing and the logic into one change here and show you that you wait until the queue is not empty. So while the queue is empty, keep delaying, stay out of that loop without delay. Then once it is not empty, you know the front is valid. You can then pull the front off, pop the front, record the front, pop the front off the queue, and then co-return. Okay, so you've taken your time, you've written a high fidelity model. You've created this coroutine system that properly represents your hardware. And hopefully you've written some tests around that, meaning you're checking the correctness of the model. These are all good things. These are all software best practices. I encourage them. After your model correctness is, shall we say, true, you validated it against the specifications that you're trying to build, then we need to talk about how you interact with that model in a meaningful and clean way that allows you, as I said on an earlier slide, to integrate with production. When I say integrate with production, I don't mean we're launching coroutines on embedded systems to do the workloads. I'm saying I'm offering you a way to produce a test infrastructure that does not require you to modify your production code. And here's the pattern. We call it register hooking. You've got your complex model, now you need to interact with it. And you create what we call a hookable register. If you go back to last year's CppCon, Ben Sachs called this a device register. Fundamentally, it's a class that has the assignment operator and the cast operator for whatever your register type is. In this example, I'm going to use uint32t. It also contains infrastructure for you to register pre-read, post-read, pre-write, and post-write side effects. So when the value shows up in the write example, you can apply a pre-write side effect to the model. You can then write the value into the model and apply a post-write side effect. Similarly, on the read, before you return the value, you apply the pre-read side effect. After you've got the value out, you apply the post-read side effect. The two extensions that we're offering in the same code pattern here to appreciate how this is a uniquely embedded concept because we're interacting with hardware have to do with, should you choose to do this with the preprocessor, there's a way to do it, and how do you handle cross-language use of this model? I want to clarify cross-language use. I'm not talking about call it in Python. I'm talking about call it in C. So if you have a preprocessor flag that determines that you're using these coroutine models that you have built, you can create a type def. And in this case, we call it IO uint32t, which simply means this is an input-output uint32t. You define all of your registers that are memory mapped that your processor would interact with as IO uint32ts. So it depends exactly how you build your register sets, but conceptually you would have structures representing each logical subdivision of your hardware. Inside those registers, you would have each register defined as an IO uint32t. What this piece of code does is it says, when you're not using the models, those are all uint32ts. That processor is going to issue loads and stores on whatever the bus is, and it's going to run. If you're using the model, you're now saying that's a hookable register. And if you compile your C code with C++, a C++ compiler, I should say, you do a little tiny compiler switch there and say, build this as C++ rather than C, and now all of your registers have become hookable registers. Why am I really taking a minute to highlight this? There are times in embedded systems development when you're required to write your production code in C. I've been there. I've been stuck in that position. Sometimes it's a matter of resources. You just don't have the memory space in the processor to be able to support the overhead of C++ objects. And you have to put so many features into such a small space that the architects or the bosses say, it's got to be in C. We've got to be super efficient in our compilations. The other way that this comes up is in certain safety scenarios. There are standards for different levels of functional safety that require you write your code in C. My intent here is not advocating for C in embedded. I actually think C++ is the better language in embedded. I'm trying to say that you shouldn't ignore what we're suggesting here as the means to generate your the means to trigger your side effects as limited only to C++ code. If you have production code in C, this is a way that you can have your C production code interact with your C++ model code. So what does that look like, integrating with the coroutine? Now, briefly, I'm demonstrating a very basic hooking, a very basic triggering of side effects. You could write the hookable register to have a subscription publication model, where you subscribe your side effect handlers to a list, they're all called, et cetera. In this case, I'm just suggesting that there's a class that has been derived from hookable register as a means of clarity in the presentation. There are more efficient implementation patterns that you could take advantage of here. And again, we're talking about the queue. So we're assigning to the register. So in the assignment operator, the register is on the left-hand side. When that occurs, we need to push into the queue that is behind it. So our side effect that we're triggering is the push operation on this queue that we were describing. So what happens when you run your code with the models, the use models flag set, you will eventually reach the point that you write to this register. Then you will call, or C++ will do its magic underneath the hood, and it will say the operator for this is overloaded, and this is the implementation that you're going to execute when that operator appears in the code. And in this case, we're telling it to wait. We're saying your write will not complete until the queue accepts the value, which might not be correct for your hardware. You could do a posted write here. You could just not wait and say, I tried to write, and then eventually it'll happen. There's probably a little more to this in the way that you actually use this in your model, where you'd probably have a fill level register that you would check before you tried to do this, otherwise you would lose data. So again, simple implementation. The practical use of this in a real model is a bit more complex and a little bit beyond the scope of what I can fit on PowerPoint slides. The return dereference this is just the pattern that operator equals expects. It expects that you will return the left-hand side, and that has to do with multiple assignment in the line. When you do the get, well, now the register is on the right-hand side, and the compiler, because I'm assuming in your production code, you're going to pull that FIFO element into a uint32t, the compiler looks at hookable register on the right-hand side, and asked what's on the left-hand side. Oh, that's a uint32t. Let's find the cast operator for hookable register to uint32t. And you define the cast operator. You could similarly do this for any number of data types. At that point, it becomes just a matter of how verbose your code is, because every data type that you do, you'll need a different assignment operator overload, and you'll need a different cast operator overload. Of note, the compiler will also try to do some of the primitive type relationships for you. So if you're trying to assign to a uint8, it will try to first find a cast for uint8. If it doesn't find that, it tries to find uint16. When it doesn't find that, it finds uint32, and then it implicitly casts it down. The compiler does a lot for you in this, which is beautiful, so long as you give it a good translation, a good cast from hookable register to some primitive type. Okay, so now you've got to kick this model off. You're going to run the model. You're going to have it start, and it probably starts a couple of things. You could think of these submits as releasing the hardware from reset. In fact, that's one of the implementations that we used. We had a hookable register that said, when I release this hardware from reset, start the coroutine that represents the state machine by submitting to the queue. That's a legitimate side effect. Just to highlight it, I used the queue coroutine side effects here as a matter of carrying the story through this slide deck. But nothing says that the side effect has to be a coroutine. The side effect can be whatever you need it to be. And as I say, when we developed our system, we said the reset bit being the release from reset side effect was to start this thread. Okay, well, you've released a couple of different hardware logical subdivisions from reset. Remember, RTL is always parallel. That's why Verilog has the always statement in it, for those of you who are familiar with what RTL looks like. RTL is always parallel. Your hardware, you have to assume your different hardware modules, the models that you've created, are all going to run in parallel. So you start up all your models, and then you wait for conditions to be met. And in our case, we're saying we're waiting for those coroutines to completely finish. But I mentioned there's back-end inspection. You could use a coroutine to intercept what's happening here. And these weights that you see at the bottom, down here, do not have to be weights on the threads that you've started. They could be weights on other coroutines related to the objects that you are starting in these threads. So this brings us to kind of the logical next thing. You've tested your model, and your model is solid. I mentioned before, we've already met the spec in the model. Now you want to test your code. So you know a test condition. You've started a piece of your simulated hardware. It's reached its done condition. The done bit's been set. Well, you can co-await on a coroutine that becomes ready when the done bit is set. You'd basically spin on that inside the coroutine. And when you have the bit set and you pop out of that while loop, you co-return. So you then have trapped your test condition. I've provided the inputs. The outputs have become ready. Let me go assert that those outputs are my expectation. You can also do inspects, as I mentioned, with other coroutines in this .get operator. Again, the .get is particular to the concurrency PP implementation, but it's a similar concept. You can have a coroutine in the object representing your hardware subdivision and have it trap the ready condition. I think it's also logical that you would have back-end inspection. You could have logging. You could have all of these features that are useful in understanding how a model behaves, all because you can implement coroutines that become ready at the right times to test those conditions. And finally, this is not something we actually did, but we know it's logically possible. One of the principal uses of coroutines in software as opposed to embedded software, not that embedded software is any less software. One of the principal uses is for I/O to external hardware to files. While you're waiting for that disk to fetch your data for you, your coroutine goes into the not ready state so something else can run. And then once the data shows up, the coroutine becomes ready again and you use your data. It's one of the more classic examples of coroutines in generic software systems. Or similarly, that could be any hardware I/O. So if you have some input-output mechanism, a card that gives you GPIO that attaches to another piece of hardware, and you wrap your coroutine model, if you design your coroutine model calls that interact with your software model, then when that piece of hardware becomes available and you attach it to your test system, and I'm assuming your test system is something like a PC, it's not a full embedded system because again, that board's somewhere down the road, then you can substitute the full simulated coroutines with the coroutines that interact with your hardware I/O elements to talk to that new piece of hardware. That gives you hardware in the loop. That's the HITL on this slide. So you can go from a full software simulation with well-designed coroutines, expecting that you will provide a different object that is actually hardware in the loop calls out to some device attached to your computer. That gets you one step closer to your final embedded system. Through all of this, you've built a progression of definitions and levels of detail. You've started with the software model that just eventually becomes ready. You've designed that model in a way that your coroutines match hardware I/O options in some future intermediate development step. That gets you one step closer. You are now simulating your code, but interacting with your new hardware element. And then finally, the board shows up, and you've already gotten all of this test coverage at these different levels of detail, different levels of depth in the edge cases. And that means you've accomplished the goal. Your software is ready when your hardware shows up. Now, I don't want to minimize the need to test on the hardware. Ultimately, the product has to work, but it at least gets you to the point where you've ironed out a lot of your edge conditions. You've handled a lot of funny things about your hardware behaviors, and perhaps you've even given your hardware designers some feedback saying, these 2 bits being in the same register are problematic to us because of a timing condition. Or this set of registers would really be easier if you reordered them for us. That's also part of hardware-software co-design. How do you use your software to make better hardware? So my takeaway message for you. I put some code on the board. I've pointed you to some examples. I've mentioned a couple of repositories. Here's what I hope you walk away with. Coroutines are a great modeling tool. This was an idea where we were figuring out how to write this new hardware model, and one of our engineers said we could do it with threads, and we said, sure, let's try it. And we did all of that threading stuff that I showed you, and it just got congested. Let's use that as the word for what the code looked like. We said, okay, let's take a minute here. We're very early in our case, we work on silicon. We're very early in a pre-silicon program. We've got the time. Let's explore an innovative option. And we looked at coroutines, and we're very glad that we did. Those coroutines make complex code easier to write because the constructs that you're using are different than normal threading constructs. And they are more amenable to representing hardware because, as I say, you can create these complex parallel interactions with relative ease. You just co-await the other part of your hardware that may be executing in parallel. Your more hardware-focused teammates will probably find that easier to read than having to mentally say, the lock was acquired here and it was released here. Oh, but wait, the lock's actually inverted, so it was released here and wait. See what I mean? I'm sure that those of us who are C++ developers could follow that logic, but part of the point that we're trying to make here is when you go into those reviews of designs, your hardware implementation teams, if they're doing RTL, will be able to read this more easily than a threaded model. It's a really cool language feature. We actually started this work right as C++20 became live. We found that GCC didn't quite do this correctly, and we had to make it work in Clang, which was different for us because our team was mostly a GCC team. I understand that support's gotten better in recent years. And you should try it. I can't guarantee that it'll work for you. There's certainly a learning curve, and you need to experiment with it a little bit to get the hang of it. But if it works for you, it creates very clean, very modern C++ code that you can use in your tests. And finally, when you look at how coroutines are typically viewed from the C++ community, they are rightly seen as a means to handle more efficient use of a processor thread related to execution workloads and the I/O that we previously mentioned. But we think we found a meaningful use case for coroutines that I hope the C++ community explores and adopts. And with that, I thank you for your time, and I will take whatever questions you may have.
Is this something you're implementing within an operating system context? Are you bare metal, RTOS? Where are you running this?
In our testing approach, we have a set of, let me back up half a step. The hardware that we're running on is not x86 servers or x86 desktops. We're running on a much smaller processor. In our testing approach, there are a set of unit tests that execute in an x86 server. And prior to this approach, we basically mocked the hardware interaction layer. We said, you get to the HAL, mock the HAL, record the side effects through some, we'll call it spaghetti code, that was limited in its ability to do side effects. So the rationale here is that quickly running tests on readily available resources, because you can always get another server, or you could always spin up another AWS instance to do more tests faster. Benefit because we can have better model definition in that environment as opposed to our more constrained environments where we're relying on actual silicon boards that are product boards, which are more expensive, harder to scale. You typically have to have somebody come in and plug things into other things and power them on. And it gives us what I would say better test throughput and better test velocity. But it's running on Linux, on an x86 box, like Ubuntu or Red Hat.
That was a great presentation. Can you go back to the slide where you're defining the queue? I think that was right around slide 32, if I recall.
This is the end of the pop.
Yeah, so wouldn't you still need a mutex around checking if it's empty and then actually getting to front?
Excellent point. I mentioned that atomicity matters, and you'd either have to do an atomic operation or you'd have to have a mutex there. After I'd put the mutex into the slide, this thing was going off the bottom, and I just conserved some space. I should have prefaced this with not all of this code is perfect, correct, and will compile. I'm trying to provide you snippets and examples to see how this could work.
Right.
You're absolutely correct.
So you would also need it on the push side as well.
Yes. Yes.
Okay.
Or you would write a thread safe queue.
Thank you.
Very interesting talk. I have the question. So for your model, actually, you described the logic in the coroutines, using the coroutines mechanism. But I assume the modeling results, they should also depend on the characteristics of this thread pool. So what are considerations are taken to select the correct amount of threads for this model?
So it's a valid concern. Like you have to have the right number of threads. Let me consider this. So in a thread pool, in our case, we use the defaults that the library provided. The way that that thread pool works in the back end is that it checks every running thread that has a coroutine in it to see what of them are ready. And we did not pay a large amount of attention to timeliness of the execution of the model. So in our case, 10 milliseconds of hardware time might have taken us a minute or two, but it was correct. We had focused on correctness. You have a very valid point that if you get to a sufficient level of complexity, you need tighter control over the threads. We use the thread pool as an ease of implementation choice when interacting with the library. The library also has the ability to spawn thread by thread, as opposed to just operating in the thread pool.
So basically, you're checking mostly the functional correctness rather than, how to say, timing aspects.
Correct. And this goes to a point that I made earlier about the delay. Let me see if I can back up to that quickly. So I make a point here that the time is virtual and fungible. So that 10 milliseconds is going to be 10 milliseconds plus the amount of time that it takes for the runtime to come back to actually switch to it or to make that coroutine ready. That means that you really can't do tight timing operations in this type of simulation. And to my earlier point about the level of detail becoming finer as you approach product readiness, you start with this very loose level of detail where it's not very timing accurate. And then you get closer to timing accuracy by doing hardware in the loop or by running on silicon emulation or silicon simulation.
Okay, thank you.
Thank you very much for the talk. You gave me a lot of very interesting things to think about. So very glad that we had you here. I was curious about, I've heard from a number of people that increasingly when they get the definitions of their hardware devices, that those are machine generated. Mm-hmm. And I wondered if that created any complications for you, if that was something that you'd dealt with.
There's essentially an industry standard called IP exact, which is a XML. And we have facilities to parse that XML into a defined pattern of structs and IOUint32s that define our register banks. So we pick that up as part of the handoff from the hardware organization to the software organization.
Okay. Thank you.
All right. Well, thank you again. I hope this leaves you with something to think about.